So first of all, how much do you guys know about recursion in general? You guys, if you know a little bit about recursion, you can type it in the chat. So how much do you guys know about recursion? Okay, well, okay, so let's basically start with what exactly is recursion then. Okay, so a recursion, a sequence with terms that depend on each other. Okay, yeah, those are all good explanations. Generally, like the easy recursions you might see on some contests are something like, for instance, Sn equals to Sn minus 1 plus Sn minus 2 over 3 or something like that. Because usually the most basic recursions you'll see, the next term is derived by some sequence of the previous terms, usually by putting in some linear coefficients in before them. This would be a second degree recursion, and this can actually in fact be solved through characteristic polynomials, which we'll be discussing later today. Okay, so, oh, did anyone have any questions? Wait, was it Kai?
Yeah.
Okay, sure.
Yeah.
Yes.
Are geometric sequences examples of recursion?
Yes, a geometric sequence will just be a recursion of the form Sn equals to C times Sn minus 1. Yeah, good observation. Yeah.
我一会儿回来要拿电脑连上，还是拿你手机看？
Oh, okay. I'll mute 这么说. Okay, so then let's start with some really basic recursions. How about a Fibonacci sequence? Okay, you guys may have already heard about what a Fibonacci sequence is. So a Fibonacci sequence, so it is a sequence defined in the following way. F1 equals to 1, F2 equals to 1, and Fn equals to Fn minus 1 plus Fn minus 2. So I will write out the first few terms of the Fibonacci sequence. It starts with 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144. Okay, so these are the first few terms. You do not necessarily need to memorize them, but of course it's good to get familiar with them so that you can easily recognize them. Okay. So first let's start with just a very easy practice problem. Suppose we have a sequence defined in the following way. Sn equals to Sn minus 1 plus Sn minus 2, and with the starting conditions of S1 equals to 5, and S6 equals to 21. Okay, so then what would S2 be equal to? Does anyone know how to solve this one? If you have any ideas, just type it in the chat. Set variable. Okay, good idea. Set variable for which ones? S2 equals to X. Yes. Okay, so basically set a variable for S2 because we do not know what S2 is. So then this is the idea. We will write S6 in terms of S1 and S2. So in order to do this, then find 21. Okay, yeah, that's basically the idea. So what we will first do is S3 is equal to S1 plus S2. Then we have S4 equals to S2 plus S3. This is because of the way the recursion is defined. And this is equal to 2S2 plus S1. Then S5 is equal to S3 plus S4. We sum these up and we get 3S2 plus 2S1. Then S6 is equal to S4 plus S5 equals to 5S2 plus 3S1. So now we can solve for what S2 is, because we are already given that S6 was 21 and S1 was equal to 5. So S2 is equal to S6 minus 3S1 over 5, which is just 6/5. Okay, so this is a rather simple recursive problem. Okay, then let's do another problem that also utilizes recursions. In this one, it will no longer be so obvious what the recursion is. If you guys can find the recursion, then please type it in the chat and also define what each term of the recursion represents. Okay, so problem 2. So the problem statement is as follows. How many ways are there to move exactly 12 units forward? Exactly 12 units forward. If the only allowed steps are steps of length 1 and 2 forward, or steps of length 1 and 2. So basically what this means is that I could start at the start point. Each time I could either move 1 step forward, or I could instead choose to move 2 steps forward. So I have 2 possible moves each time. And my goal is to move exactly 12 steps. Kyle said, yeah, it is in fact Fibonacci, but I would also, yes, the answer is Fibonacci, but I would like you to also explain like where did the Fibonacci come from? Do you know, or you've just heard that it's Fibonacci? Okay, yes, you know, then, okay, well, I'll also explain how to do this one. So why don't we first define some variable Sn? So let Sn be the number of ways to move forward exactly n units. Exactly n units. Then what do you think is the relationship between Sn and Sn minus 1 and Sn minus 2?
I think I
Aiden,
know it.
oh, you know, okay, yeah, I think what Aiden said is correct. That is basically the idea. Okay, well, yeah. Kyle, you said you know the recursive relationship.
So let's say we have like S, like we have like S n minus 2, just gonna draw a random amount.
Yeah,
Okay, sorry. Like this specific amount is S n minus 2. You can add 2 steps to it. Like the last the last the last the last
the last move you
what is
did
it called?
can be, yeah.
The last move you did is 2 steps, and then we have S n minus 1 in cases in which the last move you did is 1 step.
Yes.
And if we keep doing that too, like we can keep doing like from there, like we can do like S n minus 1 could be like some amount of S minus 2 cases where the last 2 steps were like 1 and 1, and then we could keep using recursion to like continuously, like, how to say it, to continuously repeat like and like break it down. So this S n minus 2 could be like S
Yes.
S minus n S n minus 3 cases for like the last 2 steps were 1 and then a 2, and then sorry, people. I'm using a computer. Like
Yeah, I
S
think
n minus 4 cases for like the last two steps were both the last two moves were both two steps.
yeah,
And then
but
we can keep breaking it down until we get like one.
yeah, that is a good idea. You are correct, but then I believe it is not necessary to break down Sn minus 2, because if you keep trying to break each of them down until the base case, that is not necessary. Because that will actually, if you keep going down the tree until eventually you hit the bottom, then at that point it would be equivalent to just counting each of the cases literally. So I think, but your original idea is correct. We will just stop over here because this gives us that Sn equals to Sn minus 1 plus Sn minus 2. With this, so as you said, it is because in there are only two possible last moves you could have done. Your last move could have been a move of either one step forward or two steps forward. And those two cases would correspond to Sn minus 1 and Sn minus 2. So in order to calculate the final answer, what we do is we start with the base case. We'll start with the base case of, we know that S1 is definitely equal to 1 because there is only one way to move one step. Meanwhile, S2 is equal to 2 because there are actually two ways to move two steps. Because two steps, you could either move one step, like two moves of one step, or you could just do one move of two steps. So S2 is equal to 2. S3 is equal to S1 plus 2 equals to 3. S4 equals to S2 plus S3, which is equal to 5. I will just write out all of these. If you notice, this is actually also just the Fibonacci sequence, except just shifted one step. S6 equals 13. S7 equals 21. S8 is equal to 34. S9 equal to 55. S10 equals to 89. S11 is equal to 144, and S12 is equal to 33. Okay. I'll quickly erase and write that here. Yeah. Yes. S12 is equal to 233, and that is the final answer. So generally, recursive problems involving Fibonacci do not get too complicated. The recursive sequence can usually be seen through quite easily, as long as you define your variable to be the correct quantity. Okay, so then let's get into a slightly more complicated recursion. This time we'll be talking about Catalan numbers. All right, so Catalan numbers. Okay. So let's first introduce Catalan numbers as one of the most basic examples. I think this is like one of the ways Catalan numbers is generally introduced. So let's talk about a grid. Do you guys know what a grid walk is? Yes or no?
Is it like where you like walk on like unit lines or whatever they're called?
The edges, like, so let's say when we draw the grid. So a grid
Like
walk,
only walk on like
only walk up and to the right. Like, so basically we will be discussing a grid walk. So the only moves you are allowed is either one unit right or one unit up. You only have this set of moves. And the particular grid walk we are going to talk about is, let's say, the number of ways to start from 0, 0 and end up at, let's say, some point nn, while staying under this line, as we do not want to go above this y equals to x line. I will write down all restraints. Start from 0, end at nn. and also stay under the line y equals to x, as in do not cross this line. Yeah, so this is generally how people define Catalan numbers. And the answer to this problem is called Cn. Is Cn, the nth Catalan number. Okay. How many guys have I think it's just you can't touch that line. Oh, at Cynthia, so actually you are allowed to touch the line. It's just you're not allowed to go above it. Because for instance, a grid walk that goes like, let me change the color of my line. For instance, this grid walk is allowed. Yeah. Charlie, I saw you wrote 2n choose n minus 2n choose n minus 1. That formula is correct. In fact, you could also simplify it to 2n choose n over n plus 1. Okay. Okay, so I will explain how we derive the formula for Catalan numbers.
Some of my friends is here. Actually, I only see one of my friends here.
Okay. Darren, you were unmuted earlier. Okay. Okay, so now let's talk about how the recursive relationship for Catalan numbers is derived. Okay. So when we go, so the Catalan number Cn is defined to be the number of ways to go from 0, 0 to nn while staying beneath the line of y equals to x. So then we, in order to find the recursive formula, we discuss the first point at which it meets the line y equals to x. I will draw a new graph here. 0, 0, point n. Suppose we have a grid walk, and let's say the first time it intersects, or not exactly intersect, or just the first time it touches the line is at the point I. Okay, then over here, I is like the unique first time it touches. So then how many ways are there for the line to touch, for the path to touch it for the first time at I? So first of all, if it touches for the first time at I, what that means is that in between 0, 0 and the point I, it cannot touch the y equals to x line. Okay, so what is the number of ways to go from 0, 0 to I without touching the y equals x line? Okay, do any of you have any ideas on what this value is? In fact, this is actually a Cn minus 1. Because if we think about it, how many ways are there when we talk about going from 0, 0 to I without touching the line and staying under it? What that basically means is that for our first move, because we have to stay under the line, let me change the color. Okay, because we have to stay under the line, our first move has to go from 0, 0 to 1, 0. And because we are not allowed to touch the line, so that would be equivalent to staying under the line y equals to x minus 1. Yeah, that would be equivalent to putting up a boundary over here and staying under that boundary in the rest of the cases. So it would be like staying under this boundary until at the very end and going here. Okay. Let me change my color back to black. Okay, so basically what it means is that the number of ways to go from 0, 0 to point I without even touching the y equals x line at all and staying beneath it, that is equal to the number of ways of going from 1, 0 to I minus 1, while staying under this line. But then as we notice, this is in fact just equal to the Catalan number I minus 1. It's actually just Catalan number I minus 1. Do you guys understand this part? If you guys have any questions, please ask because, okay, you understand? Okay, good. Meanwhile, then let's talk about the number of ways to go from II to NN. II to NN, so this is a triangle steps of the two legs are length n minus I, n minus I. Number of ways to go from II to NN while not crossing over this line. That's just going to be Catalan number n minus I. So thus, in this case, the number of cases is C minus 1 times C n minus I. Do you guys understand? Because Ci minus 1, this represents the number of ways to go from 0, 0 to II. Then Cn minus I represents the number of ways to go from II to NN. Okay. Well, if you guys understand this, then I think you'll understand why Cn is then equal to I equals to 1 through n, Ci minus 1, Cn minus I. This is because Ci minus 1 times Cn minus I, that was only for the case when our first intersection with the line is the point II. But then our first intersection could be anywhere from 1, 1, 2, 2, all the way to NN. So we have to iterate across all I from 1 to n. Yes, okay. So this is our recursive formula. Cn equals to I from 1 to n, Ci minus 1, Cn minus I. Okay, so but generally people do not use this recursive formula because it is extremely long and hard to calculate. Because just in order to calculate Cn, you would have to go through the product of n different pairs. Okay, so instead we'll talk about the formula for Catalan numbers. Catalan number formula. Okay, so the Catalan number formula is more interesting. We will use our original definition of Catalan numbers. If you remember, our original definition was the number of ways to go from 0, 0 to NN while staying beneath this line. Okay, so first of all, the number of ways to go from 0, 0 to go from 0, 0 to NN is in fact just 2 and choose n if we disregard the fact, if we are allowed to cross the line. Because our main constraint was just the thing about not being able to cross the line. But if we're allowed to cross the line, then it's just 2 and choose n. Because you can go, you need to totally move n steps to the right and n steps up. And so you can just take these 2 and choose n because you could go through them in like, it's just basically a question of ordering the moves. But then in the case, but then now we're going to do complementary counting. We're going to remove the cases that cross the line. So this will be done through a simple bijection. So we will try to count how many cases cross this line. So let's say from 0 to 0 to NN. So for any path that goes over this line, that means that it must contain some point on there must be some point on this path such that x is bigger than y. No, wait, no, such that y is bigger than x. There is some point on this path. Or in other words, if the path crosses y equals to x, there is some point on it such that there is some point xy such that y is equal to x plus 1. Okay. Yes. Then now we'll take the first point at which for any path that crosses the line. I will draw this point. So we'll take the first point at which it crosses this line. And let's take a look at the rest of the path. And then we will take this rest of the path. Maybe I should draw that with a different color. We will take this part of the path and we will reflect it over the red line. The red line has the equation y equals to x plus 1. So then by reflecting it, so then the path, in fact, now is a path from n minus 1, from 0, 0 to n minus 1, n plus 1. Does everyone understand? Because if this point is xy, then from xy and also y is equal to x plus 1, or we could actually just label this point as, let's say, x plus 1. Then when we go from x plus 1 to the point nn, we would be moving n minus x steps to the right and n minus x minus 1 steps up. So when we reflect it across the y equals to x plus 1 line, sorry, that should be here. Then what happens is now we basically move n minus x minus 1 steps up. Wait, no, n minus x steps up, and then n minus x minus 1 steps to the right. Let me draw the line again. Here. Okay, yeah. So in fact, so there is a bijection. Bijection between paths from 0, 0, from 0, 0 to nn that cross the line y equals x. And paths from 0, 0 to the point n minus 1, n plus 1. So again, the bijection is simply we take the first point at which it touches the line y equals x plus 1, and then we reflect the rest of the path across. Okay, so since there's a bijection, so then in order to count the number of paths from 0, 0 to nn that cross the line, all we need to do is count the number of paths from 0, 0 to n minus 1, n plus 1. And this quantity is in fact just 2n choose n minus 1. So then that means that that Catalan number n is just equal to 2n choose n minus 2n choose n minus 1. Does everyone agree with this one? Yes. Okay. So then 2n choose n minus 2n choose n minus 1. In fact, you could actually simplify it a bit into 1 over n plus 1 times 2n choose n. Oh, so Asher law, a bijection is basically, so sometimes when we try to prove that two quantities are equal, we establish a bijection, basically as in we can show that for each one within, like, let's say if we have two sets A and B, like suppose we have two sets A and B, for each event within set A, we show that it maps to exactly one event within set B. So basically, like, let's say if I can show that each event within a set A maps to exactly one event within set B, and that for each event within set B, you could also map it back uniquely to the event in set A, then in this way, we show that there are an equal number of events in set A and B. So that's what a bijection would be. Yeah, a one-to-one relation. Okay. Okay, so then this is basically about Catalan numbers. And later on in our practice section, we will also show you how to show a bijection between Catalan numbers and some other interesting problems. I think the common bijections would involve the handshake problem. This I believe will be in our later practice. Handshake problem is basically when it's a question of when we have 2n people around the table and the number of ways to for them to handshake such that no handshakes cross. And then there's also the one about parentheses, balancing parentheses. Parentheses balancing. These are like some of the most common Catalan problems. Okay, but I think we can talk about those later. For now, let's move on to the characteristic polynomials and equations. Okay. Sure, Benjamin, do you want to present?
Sure. Okay. Now that we've learned about Fibonacci and Catalan numbers, let's investigate what else we can figure out. Okay. So you may have noticed that Alex did derive. Let me see. First of all, so Alex did derive a closed form for the Catalan numbers. So right. He derived a closed form for the Catalan numbers, but he did not derive a closed form for the Fibonacci sequence. So why is this? Why is it that we are able to find a closed form for some ugly recurrence like this, shown over here, but not for one that seems so simple, as presented before? This one. Why is it that we are able to find recurrence for Catalan numbers, but not this? Okay. Well, the thing is, actually, we can find a closed form for the Fibonacci sequence and many other, and infinitely many actually, recurrences, but not all of them. And we'll go over how we do that. By, of course, showing a quick example of how exactly characteristic polynomials work. So characteristic polynomials, of course, like I mentioned before, they're used to find closed forms of linear recurrences, and they have to be linear. If they're not linear recurrences, you may not use characteristic polynomials for reasons that I will show later. Okay. So let's go back to the example of the Fibonacci sequence. So the Fibonacci sequence is defined by f of n is equal to f of n minus 1 plus f of n minus 2. And we are given the initial starting conditions that f of 0 is equal to 0 and f of 1 is equal to 1, I believe. Okay. So now we are basically tasked to find a good way to find a characteristic polynomial or find a closed form for this sort of equation. And as you can see, like if, for example, although the previous example Alex stated, including the steps, only needed f of 12, what happens if we needed something like f of 24, f of 100, for example? Then using recursion and calculating value by value would not be an efficient way, and we would have to use a closed form. Okay. And just to make sure, do all of you guys know what a closed form means? Okay. Okay, so okay, you guys all know what a closed form means. I'll just briefly state it. A closed form basically means that it is not dependent on previous terms. So instead of f of n equaling f of n plus f of n plus 2, it's equal to something like some polynomial in n, p of n, instead. So that is what a closed form is. And that is what we're trying to derive. It doesn't have to be a polynomial. It can also be exponential. And it is exponential, as we will show later. Okay, so I'll first show the method because in my opinion, the method is much more easy to understand and it's much more applicable. Even if you know as long as you know the method and how it works, then you're set for most competitions. The proof itself is a bit out of reach, but though I will show a much simpler one. Okay, so the way characteristic polynomials works is that instead of considering these as sort of recursions, we consider it as r to the n, where r is some real number. And similarly, so f of n, we let this equal r to the n. And we plug it into this equation. And what do we get? We get this equation over here, which is r to the n is equal to, remember, since all of the other f's also correspond, we get it's equal to r to the n minus 1 plus r to the n minus 2. And this is for real numbers r. Okay. So now this is where the characteristic polynomial comes in. Before, all of this was just equations. None of these are actually polynomials. And here's where we get the polynomial. When we subtract r of n, or when we subtract the rest of the terms from both sides, we get r of n minus r of n to minus 1 plus r of n minus 2 is equal to 0. And this over here is what we call the characteristic polynomial of a linear recurrence. So now, does anyone know how to solve for r? And we are assuming non-trivial solution, so I'll also just state that r is not equal to 0. This is a trivial solution. What are the non-trivial solutions to this sort of polynomial? Does anyone know any like first steps? Roots of r squared minus r minus 1. Exactly. So as Kevin mentioned, what you want to do is you essentially want to divide it by the least power. Yeah, quadratic formula, right? So you divide each of these terms by r to the n minus 2, r to the n minus 2, and r to the n minus 2. Yes, so now you can write this as r squared minus r minus 1 is equal to 0. You get this. And this is a simple quadratic to solve. You get that r is equal to 1 plus minus root 5 over 2. So r actually has two solutions. And this is something that is very important to know. Okay. So the next step of this sort of characteristic method is to we can actually already write out a closed form for this recurrence. And I'll prove on why later this can be written. But for now, I'll just give it to you and you will take it for granted, but I'll show why it is true later. So we can write f of n is equal to, let's say, some constant c1 times what we had before, r1 to the n. And then plus another c2 times r1, r2, sorry, to the n. So plugging this in, we get that our closed form is thus f of n is equal to c1 times, c1 times, we just choose an arbitrary root because it is symmetric. So we can say like 1 plus root 5 over 2 to the n. And then plus c2 times 1 minus root 5 to the n. Okay, so from here, does anyone know how to solve for these two constants? Because this is what we are left with. Because we already have an exponential function in terms of n, but we want to solve for the constants. So we are up to this step. Plug in n for small values. Yes, that is correct. So we are given before, or remember, we have initial conditions. And even if we didn't have initial conditions, we could also easily like find it. But since we are given initial conditions, we can just use them. So f of 0 equals 0, right? If we plug that in, what we get is that f of 0 is equal to c1 plus c2. And remember, f of 0 itself is equal to 0. So this just gives us c1 equals negative c2. And, oops, choose a different color. And this just gives us c1 equals negative c2. Okay. And then from using f of 1, we get that 1 is equal to c1 times 1 plus root 5 over 2 minus c2 times 1 minus root 5 over 2. Oh, sorry, this would be plus. And from here, you can just clearly plug this in to this equation. And I believe what you get is something that we call Benet's formula. So Benet's formula, so after you solve this, I'm sure most of you guys can solve this. What you guys get is that C1 should be equal to equals 1 over root 5, and C2 equals 1 over root negative 1 over root 5. Okay. So now we can plug these constants in over here, and we get the closed form of the Fibonacci sequence, Benet's formula. This gives us Benet's formula. Okay. So now that we have Benet's formula, why does this help us? How does this help us solve any general system of linear recurrences, right? Any homogeneous, non-homogeneous linear recurrence, right? I'll just quickly write it out. Yeah, so exactly. What Kevin said. We can use similar reasoning to show that we can find any of this, any polynomial of this form, or any exponential function, closed X form for this polynomial. Okay, so let's review what we did and see what at each step did we do. Okay, so here is the method for, so here's the method. I'll write it on the side. And this is the most important part. If you were to take away one thing from this lesson, this would be it. Okay. So the method for solving the system of linear recurrences is to, one, if we look over here, what we did was that we did this first sort of plug-in step, which is we substituted. So one substitute r to the n, oops, for an. So that's the first step to solving linear recurrences. I'll also erase this. Okay. And the second step, then, if we look down more, is that we actually solve for these roots. And because it's just a polynomial, solve for roots. Roots. R1 all the way to, let's just say RK. R1, R2 all the way to RK. And finally, what did we do? What was the last step that we did in order to solve this linear recurrence, right? So once we did this, we had this sort of nice form for f of n, but we still needed to solve for these constants. So that was our last step, which was to plug in constants, plug in initial values. To find the constants, C1 all the way to CK. So this is the general methodology to solving systems of linear recurrences using characteristic polynomials. This right here. Okay. And now I'll show why this works. Hopefully, I'll also give you guys a few example problems so that you guys get familiar with it. But first, I'll show you why this works. So the proof of this isn't really important because I believe it is something that is beyond the reach of competitive mathematics, and you will probably never ever have to use this. But it does. I found a simple proof that actually just uses generating functions. For those of you who knows what that is, and partial fraction. And if you don't understand some of this, it's fine, because this is just a proof. And it's much more important that you understand why and how this method works. Yes, generating functions. So it is much more important that you understand the method as opposed to the proof. Okay. So in order to use this, we will first have to, first of all, of course, set what the recurrence is, right? So we can just write, let's just say g of n. G sub n actually is equal to a1 times g of n minus 1 plus a2 times g of n minus 2 plus all the way to let's say ak times g of n minus k. So this is our recursion. This is our recursion here. And the generating function step is over here, where we write that g of x is an infinite polynomial. So this is the gen func. So g of x, we call it an infinite polynomial, which is equal to g of 0 plus g of 1 times x plus g of 2 times x squared, plus dot dot dot. So this is infinite. This goes on forever. It's just g of k times x to the k. Oh, I should have used different variables, but this goes on forever. Actually, I'll just erase it. But the point is that their subscripts are the same. Okay. So now what we essentially want is we want two ways to express g of x. Well, currently we have one way of expressing g of x, and using another way, we can actually compare these two coefficients and for each x, and that way we can actually set what each sort of a of I has to be, and what x has to be as well. So we can write out this really long polynomial a1 times g of x plus a2 times g of x, oopsies, times g of x times x plus a3 times g of x times x squared, all the way until we get to a of k times g of x times k times x to the k minus 1. Oops, let me zoom out a bit. Okay, and we claim that this is equal to g of x plus some remainder polynomial, which we denote r of x. So this is some remainder. All over x. Okay. So why is this true, right? So I guess one thing that I find helpful with this proof is to actually consider it term by term. So this first term here, right? What is this equal to if we expand it out, right? It is equal to a1 g0 plus a1 g1 x plus a1 g2 x squared plus so on and so forth. And what is the second polynomial then? The second polynomial is, actually I should use the same color. It's a2 g0x plus a2 g1 of x squared, and then plus so on. a3 it's equal to and this third one is equal to a3 times g0 x squared, and so on and so forth. And the important thing to note here is that since g of x is an infinitely long polynomial, right, and we're claiming there's a remainder polynomial, all we need to show is that for degrees of, so for terms which have degree greater than k or greater than or equal to k, that these two are the same. So left hand side and RHA right hand side are equal. And this is pretty easy to show. Why? Because as you can see here, if we continue on this process, what we get is that, for example, if we take, let's take like x to the k minus 1, right? This, if we look at the left hand side, it is equal to, so if we write the coefficient of x to the k minus 1, oopsies, which is equal to, it's equal to a1 g of k, I believe, yeah. No, a1 g of k minus 1, sorry. Plus a2 g of k minus 2 plus a3 g of k minus 3 plus all the way so on and so forth, all the way until you get let's see, a of k times g0. But what is this? Well, if we look back at how we define our recurrence, right? How we define our recurrence, this is actually exactly equal to, this is exactly equal to g of k. And hence, we have that the coefficient of x to the k minus 1 is g of k. But in g of x, the coefficient of x to the k minus 1, so for g of x over here, actually, let me do it in purple. The coefficient here, from our definition of the infinitely long polynomial, is equal to j of k minus 1. And that is exactly why we needed to divide by this x down here. Because then it helps us, it actually makes the coefficients equal. So this is just a quick sketch of why these two things are equal. So this is the important part now. So this line. Okay. Now from here, what we can say is that if you move this x over there, if you move this x over here, and you subtract g of x from both sides, what you get, and what you get is that g of x is equal to this polynomial r of x over a to the k. Oops, sorry. Okay, let me zoom in a bit. A of k times x to the k plus a of k minus 1 times x to the k minus 1. And this bit, and then all the way until a1 x plus a0. Actually, and then wait, a1 x, and then it's minus 1 because it's minus g of x, because we do not have that term here. Sorry. So this would be actually minus 1. Okay. So now what you can note is that this polynomial, right? It's the reverse of the characteristic polynomial of the sequence. Remember, the characteristic polynomial is the one that we get when you just plug in r to the n for all of these. So this polynomial over here is actually the reverse because it's 1 over that. So its roots are actually this roots like 1 over r1, 1 over r2, all the way to 1 over rk. So these are the roots of the polynomial. And what we can say is that this is the part where partial fraction decomposition works. If you haven't learned this yet, it's fine. But now we will have to use partial fraction decomposition. Decomposition is that we can factor this bottom as a series of reals, or reciprocals of the roots of the reals. So now that what this essentially means is that we can write it in this sort of form C1 over 1 minus R1, let me see, more R1x, yes, because it has to be of that form. And then plus C2 over 1 minus R2x plus all the way plus CK over 1 minus RKX. Okay. So now what you notice with each of these terms is that all of these can be written as a geometric series, because this is just a simple geometric series, like a over 1 minus r, right? This is a really simple geometric series. And that means that for each one of these, we can write it as, so let's see how we want to, yeah, okay. You can write this as, actually, it'd be better to actually replace these variables. So 1 over, sorry, c over 1 minus y is equal to c plus cy squared plus c plus cy plus cy squared plus dot dot dot, because this is just a geometric series. Okay. that means that we can write this entire thing as, once we group the terms together, we can write it as such a form: C1 plus C2 plus C3 plus dot 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 plus CK. This is the first term, and then plus the next term we have is C1 R1. Remember, because this is derived from this term over here across all the K's. Plus C2 R1 plus dot 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 plus CK R1. Well, actually, no, sorry, they should be the respective ones. So this should be C2 R2 and CK RK. Okay. And then this is times X because it has that term in it right over here. And then we have another one, which is C1 R1 squared plus C2 R2 squared, which comes from this term over here across all of them. CK RK squared. And you see where this is going, times X squared. So now, remember, this is equal to G of X. So this is equal to G of X, but we already have a way of expressing G of X. This is one way to express G of X. But we also have the infinitely long polynomial way, which was over here. And hence, if we compare these two coefficients, what we essentially get is that we can express all of these sort of roots as we can write G of n as Cn times r to the n plus C2 times r, oh well, C to the n minus 1 times r to the n minus 1 plus all the way to CK times RK, which is what we want because this is exactly the closed form, because this is a closed form of the polynomial now. So this just shows why this method works, why characteristic polynomials work for all polynomials. So we have shown that it works for all linear recurrence relations. Okay. So again, this isn't really that important. However, what is important is the fact that you know how to use characteristic polynomials. So I think I'll just provide one quick example since we're running a bit low on time. But I'll provide a quick example and then we'll move on. Okay. Okay. So let me just provide a quick example down here. Okay, I'll do a pretty simple example, I think. This only has one term, so it's easier for you to calculate. Or actually, you know what, I'll do a two-term one. So let's do, let me think. A of n is equal to A of n minus 1 plus 6 times A of n minus 2. And you are given that, let's just say A0 equals 0, and A1 is equal to 1. Yeah, sure, why not? Yes, this should work. Okay. So I'll give you like maybe 2 minutes, or I'll give you like maybe a minute to think about this, but this should be a direct application of characteristic polynomials. Yeah, so you want to find a closed form for this. I'm not too sure what it is as well. I just wrote it out. I just made it up on the spot. So it may or may not be easy to solve. Okay, I think we can try to solve it as well. So the first step, of course, like we said, so this is step 1. minus 1, 1 plus. Okay. So step 1 is to replace all of a of n with r to the n. Oops, sorry, r to the n. So we'll get that r to the n minus r to the n minus 1 minus 6 r to the n minus 2 is equal to 0. And this is our characteristic polynomial again. So this is the characteristic polynomial. And from here, can someone tell me what r is? Anyone? R equals 3, -2. Yeah. Okay. So yeah, it's just a basic quadratic. R squared minus r minus 6 equals 0. So the roots are r equals 3 and r equals -2. Yeah, r can equal 0. But the reason why that doesn't matter in this situation, that's a good point. And the reason why it doesn't matter is because of what we wrote here. So it can be expressed basically as, oh wow, okay. It can basically be expressed as this sort of a form, right? So if we had like another root, let's say it was like r3, plus c3 r3 to the n. But if r3 was 0, then it doesn't matter. This term just becomes 0. So even if r of I was equal to 0, so this is if so it doesn't matter whether or not there's a 0, whether or not there's repeated roots of 0, because those terms just go to 0 anyways. Does that sort of make sense? That's why we can just divide it by r to the n minus 2 here. So you are right. There is this trivial root r equals 0, but this does not affect our final result. So then we can just quickly write a of n is equal to like c1 times 3 to the n plus c2 times -2 to the n. And then you just use the plug in these initial conditions that we explained before to solve. These two. Oops, sorry. You plug in these two initial conditions and you solve it. And I think Alex told me that it should be a of n is equal to 1/5 times 3 to the n, and then minus -2 minus 1/5 -2 to that. Does everyone understand how this method works and why it works? Most computational questions that require characteristic polynomials in competitive mathematics typically aren't that difficult. They may be involved like a quadratic, at most a cubic. I've seen maybe 1 cubic before. But it does speed up things a lot, especially when you need to calculate large recurrences. Yes, the characteristic polynomial is this or that. But oh, okay. I guess it must be of least degree, so it has to be that. Yeah, okay, it has to be of least degree. Okay. All right. I guess we'll begin moving into the practice problems, and hopefully we'll give you a shot at trying to use these ideas and sort of concepts to advance your competitive mathematics knowledge.
Okay, guys, so let's start with some practice problems. Okay, this should be a simple recursion exercise. So let's start with problem 1. Okay. So then the question will be, let's say we're given a sequence, U3 equals to 5, U6 equals to 89, UN plus 2 equals to 3 UN plus 1 minus UN. And the question is compute U7. Does anyone have any ideas on how to solve this one? It is actually sort of similar to one of the earlier ones we've done. Assign variable. Okay, yeah, has anyone solved it yet? Okay. Kyle John, yes, Kyle John, you are correct. It is 233. Okay, I actually had a slightly different idea for this one. For this one over here, we know that U6 is equal to 3U5 minus U4. And we also have that U5 is equal to 3U4 minus U3. So we have these two equations. And then in fact, by multiplying the first equation by 3 and adding up to the second equation, what we can get is that equation 1 times 3 plus equation 2. So 3U6 plus U5, that is going to be equal to 9U5 minus U3. So we can simplify this equation with the values we were given. Basically plug in U3 equals 5, U6 equals to 89. And then with this, what we can get is that U5 is equal to 34. Then hence we can get that U7 is equal to 3 times 89 minus 34. So that is 233. Okay. Yeah, the first problem is not too bad. Then okay. So Benjamin, would you like to present the second one?
Sure. Okay. Okay, so the second problem, let me grab it real quick. It has this for sort of problem statement. Let me see. We copied it. Okay. Oh, there's an answer. Oh, well. Okay, you guys already saw the answer. It's okay. But anyways, I'll just quickly illustrate what this question is basically saying. So currently there are 10 equally spaced points on a circle labeled AB. Yes, the answer is 42. Okay. Okay. Yeah, sorry, the answer was already provided. But anyways, so there are 10 equally spaced points on a circle labeled A, B, C, D. I'll just quickly mark them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. I won't label them. Well, I'll label A, but I won't label the rest of them. And you want to drive 5 non-intersecting chords within the circle. And you're asked how many ways can you do this? Calvin, somebody said Calvin. Yes, it is a Calvin. And the main part of the proof is actually showing that it is a bijection to the Calvin sequence. So what you notice first is that if there exists, so if we already have a sort of construction, right? So valid construction must have this node A or this point A connected to some other node on this circle. And let's just say it was like this node over here, for example. Then we have this chord is a part of the circle. Actually, let me erase. I don't know why I wrote that. Okay. So now what you notice is that what have we simplified the problem down to? Now, does anyone see it? So we drew in this sort of segment within 2 points on the circle. What is now restricted? The left and the right. Why is it restricted? Yeah, 2 left points must be paired and 2 right points must be paired. Yes, exactly. We can't have something like this because if we add 1, so it splits the circle into 2 portions. Let me see how this can be more easily illustrated. So this actually splits the circle into two portions. So this left portion, let's label as left and right. And now we see that we cannot have a point that is on a left portion and a right portion at the same time, because then it would intersect, which contradicts what we have. So what this means is that we can only connect sections from the left sections or sections from the right from 2 points from the right section. And if you see here, in this specific example, so since this is a recursion, right, we can pretty much guess that it will be related to recursion. So let's just denote this as like C of 10 first. So what you know is that after we use 2 points, right, in this specific example, we have 2 points on the left. So this would be C of 2, because we want to pair 2 points on the left section, which is C of 2 ways to do that. So we say that C of 2n actually. Ooh, I should make this definition at the top actually. C of 2n is the number of ways to draw and segments non-intersecting. Okay, so it's clearly C of 10 over here is equal to C of 2 plus C of 2 times C of 8, sorry, because it's the number of ways to draw both sections. But then there's also different ways that you could connect it. For example, if I erase all this, sorry, okay, I accidentally erased the circle. We draw this, but this time instead we connect, let's say, these 2 points. Then, well, actually, we cannot connect these 2 points because there would be an odd number of circles on this side, which is impossible. So we actually have to connect maybe, let's say, these 2 points over here. Then we know that this side has 4, and this side also has 4. Also, this should not be C8, sorry, this should be C6. And then plus C4 times C4. And then once again, another one for, let's just say, this segment over here, because it divides into 2 sections again. So this is, again, plus C2, C8. Or C6, C2 this time, because if we're considering left and right orientation. So this basically just means that C of 2n is the sum of I equals, oh, there's also one cases such as these, where process two adjacent, and then you have 8 left. So we also have to add like plus C of 8, and this is technically C of 0 as well, and then plus C of 8, C of 0. I remember the points are labeled, so rotations and reflections are considered distinct. So we have this is equal to 0 all the way to n of C of 2i times C of let's see, 2n minus 2i. Yeah. So this is the recurrence relation that we have. And if you remember before, this is just exactly what, this is basically the same thing as the Cadman numbers, except we have to use a substitution that 2n equals k. So this is the substitution. And this basically gives us that this is just C of 5, which we can compute easily to be 42. Okay, does this solution make sense to everyone? And by the way, if you do not know Cadman numbers and you do not remember the closed form, it is not that hard to compute C0 all the way to C10. Okay. Let me copy over the next question. Okay. All right. So now we have problem 3. We are running a bit short on time, so I'll quickly go over this one. This one isn't too bad, I think. Sorry, where's my phone? Okay. So the figure below, let me copy the figure, sorry, shows a ring that it consists of 6 sections. And this person and you have 4 colors to paint these 6 sections in, sorry. And yes, this is a past AIME problem. It's pretty well known, I think, and especially in terms of requirements. And you have 4 paint colors available, and you want to paint each of these 6 sections of a solid color. And you want to find the number of ways you can choose to paint the sections if no 2 adjacent sections can be painted with the same color. So let's first see just why direct counting won't work, right? If we set this one to have 4 colors, right? And we try to continue onwards, this one has 3 colors over here. This one might have like, let's say 2 colors. This one once again has 3 colors, sorry. Because this color is used, but adjacent to no other colors. This one also has 3 colors. This one again has 3 colors. This one has 3 colors. Not necessarily though. So once you're done with 5 of the 4 sections, this one, it depends on what is the parity between these two. So if these two have the same color, then this one has 3 sections. But these two have differing colors, then this one only has 2 options. Or 2. Oh, sorry, don't say something. Okay, wait, sorry, okay. And or 2. You're right, or. Wait. Or 2. Okay. So this is why it doesn't work, why direct counting doesn't work. However, we can actually build off of this idea to sort of consider what we would need in order to sort of form this idea. So remember, it doesn't work because we are considering why these 2 colors are different or whether or not they're the same, right? So let's try to extend on that idea. So given that we have like a constructions for, let's say a ring of, say this time we only have five rings. So let me just quickly draw an annulus. 5. This time we only have 5 rings. How can we form a 6th ring? So let's say the colors, they're already in a good position. I'm just gonna color it randomly. How can we turn this into a 6th ring? Does anyone see a method? Actually, there's 2 ways to turn this into a valid 6th ring. Does anyone see it? Anyone? Let's see. I'll give you a moment to think about this because think about it. You want a 5 ring and you want to add 1 more section in order to make it a valid 6 ring. So there are actually quite a few ways you can do this. Actually, to be specific, there are 2 ways. Yes, Kyle?
Fibonacci?
Oh, not necessarily. Okay. So actually what you notice is that to make this into a 6 ring, right? We have 2 options here. The first option is to choose a sort of a section and we insert another color. We insert another ring. Another ring here. That is different from the 2 colors. Which is different from the 2 colors. From those 2 colors. Or the second method, which is actually much more obscure. Well, actually, this has to be with a 4 ring this time. So now let's say we have a 4 ring. This is going to be a 4 ring. And how can we turn this into a 6 ring? Well, a similar method tells us that actually, if we color it like such, oops. Let's say these were the 4 colors used. Then we can also form it into a 6 ring by considering what happens if we essentially, let me see if I can model this easily. Oh, I can't. Okay. Instead, what we do is we sort of insert one within the color. Let me see what's the best way to draw this. So we essentially split this into two more sections. And then in this middle section, we insert a new color. So the way that this would basically work is that you imagine you sort of break it in half and then you open it. So you sort of, let's see, maybe that's a better way to draw it. So essentially you break it in half, you break this piece in half, and now you're left with maybe a broken ring that looks something like this. It's green on either side, but then there's also missing some. So let's draw it out. So it's like green on this side, green on this side, because it was broken in half. And then you have the rest of the remaining colors. And then in order to make this a 6 ring, so remember now, this is actually a 5 ring because you broke it in half. So now you have to insert a new sort of color here. And there's 3 ways to do this because those two colors are the same. So there's 3 colors that work. So now you have a recurrence relation, and it should not be hard to find what the actual solution is. So the recurrence relation is, therefore, if we let it denote like a of n, it's equal to 2 times a of n minus 1 plus 3 times a of n minus 2. This is a recurrence relation, and you can solve this with the initial conditions like a1. No, you can't even use a1. You have to use a2 is equal to, a2 should be equal to 12. And you can continue on from there. A1, there also probably is a value for a1. Actually, a1 should be equal to 4, I think. Though it might also be equal to 0 if it's considered adjacent to itself. But this shouldn't be hard to show. And from there, you can easily compute the value of a6. And what you get is that a6. Oopsies. Why are there 3 ways for? Oh, because you can insert 3 colors in between. So once you break it in half, you can insert 3 colors into the slot, if that makes sense. And for this one, remember, so for this one, you aren't breaking it. No, for the n equals 5 case, you're inserting it. So those 2 colors already have to be different. So when you insert, there's only 2 colors. Okay. And from this, you just calculate that n a of 6 is equal to 732, which should be your final answer. Okay. Alex, would you like to go over the last question?
Yes. Okay, so we might go over time a little bit, but okay, so problem 4. So this will be a bit of a challenge problem. I don't expect you to be able to solve this very quickly. So x1 equals to 0, and xn is equal to root xn minus 1 plus 1 over 2. So this isn't exactly your normal recurrence. You'll actually need to find some interesting way to solve it. Okay. Does anyone have any ideas for what the general term of xn will look like? Any ideas? Like you can first calculate the first couple terms, but there won't be any obvious pattern. Because what we'll get is we have x1 equals 0. Root 1 over 2. No ideas? Okay, so then I'll give a little hint. When you look at xn equals to root xn plus 1 over 2, what we can turn this one into is 2 times xn squared minus 1 is equal to xn minus 1. Okay, now does the 2xn squared minus 1, does this remind you of anything? Oh yeah, that question is to find the closed form of xn. Yeah. Okay, so yeah, exactly, Daniel, you're correct. It is cosine double angle. So then maybe you guys now see that this is in fact the cosine half angle formula. This is cosine half angle formula. Okay, so now in order to do this problem, what we'll do is, let's say if xn is equal to cosine of theta n, we can set xn. So clearly we have cosine x1 is equal to theta 1 is equal to pi over 2 because of the initial condition x1 equals to 0. Like x0 is cosine of pi over 2. And then we notice that over here xn, because it's xn minus 1 plus 1 over 2, that is in fact cosine of theta n minus 1 plus 1 over 2. And this is going to be equal to cosine of theta n minus 1 over 2. So since we have theta 1 is equal, so thus what this means is that because xn, this is cosine theta n. So then this means that theta n is equal to theta n minus 1 over 2. So then since theta 1 is equal to pi over 2, so then theta 2 is equal to pi over 4, theta 3 is equal to pi over 8, and so on. And we can use the relationship theta n equals theta n minus 1 over 2. This is in fact a geometric relationship. And we see theta n is equal to pi over 2 to the n. Okay, so then thus this means that xn is in fact equal to cosine of pi over 2 to the n. Okay, this is actually a really challenging problem, but the main motivation behind this one is you have to it would be best to first simplify the expression, and we notice that this thing suspiciously looks like the double angle formula, and then we realize that in fact it is the double angle formula, and then this can motivate us to use cosine. Yeah, Kevin, yeah, no, the final answer is actually 2 to the nth, but yeah, you were close. Okay, right now, as like a final question for you guys to think about, I'll leave like one more problem. This question, it is, so a1 equals to 1, an plus 1 is equal to 1/16 of 1 plus 4 an plus root 1 plus 24 an. This one is actually not trig. Do you guys think you can find the closed form of an? The main thing you guys need to be worried about is the square root 1 plus 24 an term. Does anyone have any ideas about how to handle this one? Square both sides. Yeah, that's a good idea. Okay, any other ideas? No, okay then. So basically my idea was set bn equals to root 1 plus 24 an. Because we want to actually remove the square root. So in this case, we just set bn to be equal to it. Then we can write this as, so then over here, then we have bn squared is equal to 1 plus 24 an. And this is in fact going to be equal to 1 plus 24 over 16 times of 1 plus 4 an minus 1 plus square root of 1 plus 24 an minus 1. This part is derived from this recursive relationship because we can replace the an with this part. And that is in fact because 1 plus 24 an minus 1, this part can be replaced with a bn minus 1. And the 4 an minus 1, you could also replace it with a bn minus 1 squared in this term. And in fact, we can see that when we simplify this, this becomes 1/4 of 3 plus bn minus 1 squared. Okay, wait, it was because the 4 an minus 1, let me just write this one as, bn minus 1 squared minus 1 divided by 6. Okay. So because now we have this expression, bn squared is equal to 1/4 of 3 plus bn minus 1 squared. Let me rewrite this. Bn squared equals to 1/4 of 3 plus bn minus 1 squared. And since we noticed that both sides are perfect squares, we can in fact turn it into bn equals to 1/2 of 3 plus bn minus 1. Okay, does anyone know how to solve this one? Because right now it is already linear. Characteristic polynomial, no, it will not work over here. Because for a characteristic polynomial, usually, because characteristic, you cannot have any constants. Because a characteristic, you would have to have something like bn equals to c1, bn minus 1 plus c2, bn minus 2. But the problem over here is we have this constant term of 3. So characteristic doesn't necessarily work. Okay. Bn equals to negative 1/2 plus 3n over 2. Oh, actually, that is not correct either. Because actually, this is geometric, because if we notice that every time you multiply by 1/2, it's going to look, oh, Jeremy Bell, well, over time, but since we started a bit later, I think we'll be ending in just like 3 minutes or so. Okay, so I think now it's time to also go over an important technique over here. Bn equals to 1/2 3 plus bn minus 1. It looks rather difficult to solve, but then we can do a very simple trick over here. First of all, it was 1/2 bn minus 1 plus 3 over 2. If we minus 3 from both sides, what we would get is bn minus 3 is equal to 1/2 times of bn minus 1 minus 3. Yeah, so this is a very good trick, because now if we, like, let's say set something equals to bn, set cn equals to bn minus 3, then cn is equal to 1/2 of cn minus 1. So this is clearly a geometric sequence now. Because then you can get cn is equal to 1/2 to the n minus 1 times c1. Well, actually, you could just write it as bn is equal to 3 plus 1/2 to the n minus 1 times of b1 minus 3. Yeah. So then this is our recurrence relationship. In order to find our answer, we go back to what the original one was. Originally, we had a1 is equal to 1, right? Because we had a1 equals to 1, we can quickly solve it. a1 was equal to 1, b1 was root 1 plus 24, a1 equals to 5. Okay, so thus we would have the recursive relationship bn is equal to 3 plus 1/2 to the n minus 1 times of b1 minus 3, which is just 2. Okay, then in order to get an is going to be equal to b1 squared minus 1 divided by 24, and bn squared minus 1 over 24. And this we can get by directly solving. And I believe what our final answer will look like is 1/3 plus 1 over 2 to the nth plus 1 over 3 times 2 to the 2n minus 1. Of course, the final answer isn't as important as the technique of how we solved it. One of the most important techniques introduced here is this part, because if you encounter something like bn equals to, let's say, some constant times equals to some coefficient times bn minus 1 plus some constant, what you should do is you should try to add or subtract some special constant from both sides so that you can turn it into a geometric sequence. Yeah, this is a really interesting problem. I really like this one. Okay, this one is our final answer. Yeah. Okay. So yes, this is the end of our class. After class, we will also send the recording and the handout. The handout will also include a homework around 5. Yeah, there are 3 homework and 2 challenge problems. We highly encourage everyone to also try the challenge problems. And if you guys are stuck on homework or have any questions about this class, we will be hosting office hours on Saturday at 4 o'clock. So anyone who has questions can come to ask. Okay. So I guess this is the end of the class now. Okay, bye. Okay.
Bye.
Bye.